All right, so today we are talking about 6.3, which is a section called inverse trigonometric functions. And that's something that we actually started to talk about last Monday, where we were saying, okay, now we're going to find angles on our unit circle as opposed to finding coordinates. And so I just want to go over this chart real quickly, and maybe folks can help me fill this out, because I think one of the biggest challenges in trigonometry is there's more than one way to say the same thing. And so sometimes we only know one of those ways, and then that's not the way that's helpful to answer the question, and we kind of get stuck. Okay. So let's start with the ones that we've been working with the longest. Let's start with the main trig functions. And so what is the first main trig function that we normally list when we're listing out all of them?
Sine.
Exactly. We list out sine, right? And so we have sine of theta, right? We need to have some sort of angle there. But what is one thing we can say that sine theta is equal to?
Y.
It is equal to y, and maybe more specifically, like the y values on the unit circle. I agree with that. All right. What else can we use to say sine? Yep, Matthew, I agree with you. We can say opposite over hypotenuse. And Avi, I'm not sure what you mean by pi.
Sorry, I was thinking in values of the unit circle rather than, I was thinking of the angles rather than the values. Oops.
Okay. Okay. All right, so we've got sine of theta is 0 or opposite over hypotenuse, or as Ellie said, we could also say that it's equal to y. And so knowing that we could write it two different ways is really important here. Okay. I think one of the things that maybe as we're going through this, I know that some of us might choose to maybe not take notes because, you know, I provide those notes afterwards. But I think sometimes when we spend that time writing it ourselves, even if it's not neat, we actually engage with that content a little bit more. It becomes a little bit stickier. Okay. All right. What do we say after sine? Or what's the next trig function that we usually think about?
Cosine.
Exactly. So we have cosine theta. And what are two ways that we could write cosine theta?
X.
We could say x, and what else could we say? Perfect. All right, so we got adjacent over hypotenuse, and we get x. Great. Last one here. Perfect. We've got tangent theta. And what are two ways that maybe we can write tangent theta? Perfect. All right, so we've got opposite over adjacent, or we can say y over x, right? So those are the main trig functions. And from the main trig functions, we talked about these reciprocal trig functions, right? So let's kind of build that list. If we start with sine, what do we have as the reciprocal function for sine? Great. Cosecant theta. We need that angle there again. And what are two ways that we can write cosecant theta? Perfect. Hypotenuse over opposite is 1. And alternatively?
1 over y.
Perfect. 1 over y. Great. All right. What is the reciprocal function of cosine? Perfect. We've got secant theta. And how can we represent that in two different ways? Good. Hypotenuse over adjacent, or alternatively, we could say
1 over x.
1 over x. You got it. All right, last one here, the reciprocal of tangent. Perfect, cotangent of theta. And we can represent that in two different ways. Adjacent over opposite, perfect, or
X over Y.
X over Y, beautiful. Okay. So before we move on to the other ones, let's just talk about when we might use which one. So can someone tell me a kind of problem where you would maybe want to use sine of theta equals opposite over hypotenuse and you wouldn't want to use Y?
If you're trying to find like the opposite side of a triangle from an angle.
I love that. I love that. Yeah. So when we talk about sides of the triangle, like opposite over hypotenuse, adjacent over hypotenuse, or opposite over adjacent, those ways of writing sine, cosine, and tangent are probably really useful when we're looking at right triangles, right? Like we literally see a right triangle, or it's like a word problem kind of situation, okay? Now notice, I'm not writing this down, I'm saying this out loud, but this is a great place for you to make a note and say, oh, when I see opposite over hypotenuse, I want to use that for like a right triangle situation, right? I would write that down for myself so I can sort of make those decisions in advance before I get to an exam, okay? So then separately, when would you use X, Y, or Y over X? Like if someone says, oh, tell me how to say sine, cosine, or tangent, when would you use the Y, X, and the Y over X? Yeah, when we're looking at unit circle problems, right? The unit circles where we have all those coordinates, like an X coordinate, a Y coordinate, a Y over X that we have to reduce and get a value for, right? So yes, there's a lot of different representations, but also knowing when you know to use which one is really valuable, okay? So when we talk about sides of a triangle, we're probably thinking it's like a word problem or a right triangle problem. But if we have a unit circle question, then maybe we want to use the X and the Y over X, okay? All right, let's talk about these inverse trig functions now. So the inverse trig functions, we talked about last Monday. What is the one that goes with sine of theta? Perfect. All right. And just so we're clear, that sine with the -1, we say is inverse sine. So sine with a -1, we say inverse sine. All right. And what do we put inside those parentheses? O over H for sure. Okay. Opposite over hypotenuse. What else could we put inside the parentheses? Yes, we could put Y, okay? So now let me maybe talk this out a little bit more. If I had a right triangle problem, I might use this one. But if I had a unit circle problem, I might use this one. All right, so that same decision making still applies. Either way, what is our answer going to be? Like, what kind of number will our answer be? It's going to be an angle, exactly. Okay, so in the inverse trig function category, we're going to have an angle as an answer. All right. So if I were to write a similar statement for cosine, I would write inverse cosine of adjacent over hypotenuse, or I could say inverse cosine of x if I was looking at a unit circle problem. And either way, my answer would be theta or an angle. All right. And similarly, inverse tangent would be opposite over hypotenuse, or I could say inverse tangent of y over x, and that will equal some angle. All right. And so these were the three that I was like, the three categories of trig functions that we're going to be working so much with. Okay. There is a category, the column right all the way to the left. I only wanted to bring this up because someone had asked about it in class, but we're not going to be using this in our class. And so I just want to make a note way down here that we will not use these, right? In fact, I'm not really sure that I've ever seen it used in practice, but conceptually it exists. And so I felt like it was necessary to kind of talk about. But we could write inverse cosecant, like that's a thing, inverse cosecant, and it would be hypotenuse over opposite. Or we could say inverse cosecant of 1 over y. And either way, my answer would be an angle. Okay. So just like the regular inverse trig functions, we could have inverse reciprocal trig function. So we could do secant inverse hypotenuse over adjacent, or inverse secant of 1 over x, and that would give us an angle. And finally, inverse cotangent would be taking the adjacent and opposite sides, or x over y, and either way, our answer would be an angle. Okay, so that blue column is really there for those of us who are kind of curious, like, what other things can we do? There's like so many more things we can do, okay? But in the context of this course, these three categories are the most important to be familiar with, okay? All right, so let's do this. I'm gonna ask you to, go ahead and open up Desmos or a calculator if you have one. We're gonna talk through two quick examples about how we use our calculator to find different values, okay? But if you don't have a calculator, there is Desmos that I just dropped the link in the chat for that you can also use, okay? And so let's talk about the applications of the inverse trig function first. Like, what do we even need them for? All right. And so we've got this example here. A person flying a kite has released 176 meters of string. The string makes an angle of 27 degrees with the ground. How high is the kite? And how far away is the kite horizontally? Okay. So let's go ahead and draw a picture to match this. All right. So we'll go ahead and draw, whoops. A right-ish triangle. We'll make that there. So now we know it's a right triangle. And let's think about labeling things. All right. So based on this problem, maybe let's start with the very first number that we see. Where would 176 go? Okay. And so that would go right over here, right? That would be our hypotenuse for sure, right? Because that's where the string of the kite is, right? Because we, in theory, have a kite up here and it's attached to someone on the ground. And so all of that is the string, right? Let's move on to the next number we see. We see the string makes an angle of 27 degrees with the ground. Where does the 27 degrees go?
At the right bottom angle.
The right bottom angle. Yes, I agree. So we'll take this angle and that'll be 27 degrees. Okay. Now you might see this also written like in a word problem. Someone might call this your angle of elevation. Okay. One thing to notice, the angle of elevation is wherever the horizontal is, we measure up from that. So we're elevating from the horizontal. Okay. All right. Well, in boring, but you know, gets the job done fashion, I'm going to label this bottom side here X because it's horizontal, and I'm going to name the vertical side Y. But how would I label them in terms of like opposite and adjacent? Which one would be which? Good. X would be the adjacent side, right? It is next to that angle that we're looking at. Perfect. And that would make this Y the opposite side. Okay. Perfect. Now, it would be really important as you prepare for Wednesday's exam to make sure that you know how to label the triangle. All right. A lot of us lost some points on some of the quizzes because we didn't label the triangle correctly, which meant that all of our numbers were therefore incorrect. All right. So please make sure you are labeling the opposite, the hypotenuse, and the adjacent appropriately. All right. So which one do we want to find first? Do we want to find X first, or do we want to find Y first? All right, let's go ahead and find Y. So to find Y, all right, how do we approach this? You folks tell me.
We can use sine to find it because we have the value of the hypotenuse.
I love the way you said that. We want to find the Y. We have the hypotenuse. Look at what letters we have: opposite and hypotenuse, right? And so maybe a really good first line is to write sine of theta equals opposite over hypotenuse. And then we can fill in the numbers with what Dallas has written. So sine of 27 degrees, degrees equals Y over 176. All right. I do want us to isolate the variable first before we start typing things into a calculator. How will I get Y by itself first? Or opposite, whichever one you choose to write. How do I get that Y all by itself?
You can pass 176 multiplying to the other side.
Good, good, good. So I'm going to write Y equals 176 times sine of 27 degrees. Okay. If you did not have a calculator and then I said, give me an exact value, this would be totally fine. Right? If we do have access to a calculator, all right, so let's go ahead and see if we can find a value for this. And let's round to 3 decimal places. All right, so take whatever calculator you have available, whether that be the Desmos in the link that I just sent out, or whether that be a calculator that you have at home. But go ahead and see, rounded to 3 decimal places, what is the value for Y? All right, and when you get your values, go ahead and type those into the chat. All right, I see a 79.902. Anybody confirm or deny that answer? It's always good to double check. All right. Perfect. All right. Is anyone getting 168 point something? Okay. So those of you who are getting 168, all right. If you're using Desmos or you're using any calculator, one of the things that is super important is what mode are you in, okay? And so in particular, notice that I made a really big deal about writing in that degree symbol all the way through. I want to be in degrees, which is usually abbreviated DEG. I do not want to be in radians. Okay, so no radians, but yes to degrees. So if you're using Desmos, the way that you change that is you go to your graph setting, which is like the little wrench in the top right corner. You're going to go all the way down to the bottom of that menu, and it should say degrees and radians. If you click the degrees one, then that should change answers to be that 79.9021. Okay. All right. So make sure that we know how to change those degrees and radians. I will bring calculators to the exam on Wednesday. If you come early during office hours, you can play around with the calculators just to make sure you know how to use the degrees and radians mode there, all right? But also know that part of this exam will not be calculator. So knowing how to use these values or find nice values from a unit circle would be really important, okay? Let's say that instead of sine 27, in your question, it said sine of 30. And you had no calculator. Sine of 30 degrees is a value from your unit circle. So whatever value that is on your unit circle, you could go ahead and plug that in here. And then you could multiply out whatever you need. Okay, so if you don't have access to a calculator, it's likely that it's not going to be a weird value like sine of 27, but maybe something like sine of 30 or sine of 45 or sine of 60. Okay.
In that case, we would be working with radians.
Nope. If I said sine of 30 degrees, you can still find, you go to 30 degrees and you find the y value, same thing.
But though, like, if we're finding the y value, then we would use 1/2.
Exactly. Yep.
Oh, okay. I thought we were gonna use the radians.
So radian, so in except for word problems, like the word problems, we pretty much always use degrees, but everything else we usually use radians. That's why I've been pushing so hard for us to practice the radians. It doesn't mean it's the only way to do it though. Okay. Yeah. All right. One last thing here. Let's get some units on this value. What units should we put on this 79.902? Meters. Perfect. Great. So we'll have meters. Now we can box off our answer and we are good to go. Okay. So that's finding y. Now let's go ahead and find x. Find x. All right. So take a moment, think about what trig values we want to use. Do we want to use sine? Do we want to use cosine? Do we want to use tangent? What do we want?
We're using the cosine because we have hypotenuse and we're finding the adjacent.
Perfect. I see A and H. So cosine would be a wonderful guess. Okay. And we can fill in the values that we have. Cosine of 27 degrees equals x over 176, right? So same idea here. How do I isolate the x? Good. So we'll get x equals 176 times cosine of 27 degrees. All right, so exact value right here, but if we want an approximate value, we put that into the calculator and we round to 3 decimal places. All right, you should be in the proper mode now because we had just changed it to degrees, right? Let's see what values we're getting and if we can get a few folks to confirm. Yep, that's what I'm getting, I think. Perfect, good. 156.817. And the units for that also going to be meters, all right? All right, so we've seen this kind of question before, right? I wanted us to do it as a review because we are going to see, this is a skill that we want to know how to do for the exam, but also just a really important decision-making skill to have, right? But let's move on to another example where maybe some of the setup is the same, but now we're looking for something different, right? So let's read example 2. A 5-foot ladder leans against the wall and the base of the ladder is 2 feet away from the wall. What is the angle between the ladder and the wall? Okay, so let's go ahead and draw a picture here. We've got a wall, we have the ground, and we have a ladder. Okay. And so let's go ahead and label some things. All right. Where would I find the 5? Where would I label that 5? So you're saying that the 5 would go down here? Ah, okay. Why does it represent the hypotenuse?
Because it's the length of the ladder and it's leaning up against like the wall and the ground. So it would be the diagonal line.
Yep, exactly. All right, so we're going to label this side as 5. All right. And let's see, 5-foot ladder leans against the wall and the base of the ladder is 2 feet away from the wall. Where do we label the 2? Perfect, so we'll have 2. Okay, and then the question says, what is the angle between the ladder and the wall? So where, my friends, should I put the theta? At the right bottom, like right here? We agree, do we disagree? All right, well, I disagree with you.
I was gonna say, since it's between the ladder and the wall, it would go like at the top between the wall and the ladder.
Yeah. So what is the angle between the ladder and the wall, right? This theta would be like the angle between the ladder and the ground, which is most often the angle we get asked for. But I wrote this question this way on purpose because I wanted us to really understand, like, where do we put things? Not just like, oh, the angle always goes here, so I'm just going to put it there. Okay. So intentionally written in a way that I want us to read, that theta goes up there. All right. So if that's where theta is to the opposite or the adjacent side. Yeah, this is going to be the opposite side. Okay. That would mean that y would be the adjacent side if I needed to find it. Okay, we don't need that in this problem, but I just wanted to write that there because, you know, going into this exam on Wednesday, some of the stuff we learned like 2 weeks ago, right? And so I just want to refresh us on that. Okay, but one point I want to make before we move through the question is that in the previous question, I said that this angle was the angle of elevation. And this is also a very common mistake that I had on a recent quiz as well. A lot of people lost points because they didn't label the right angle when it said angle of depression. Okay. This angle right here between the ladder and the wall is not the angle of depression. All right. This is not the angle of depression. What is an angle of depression then? Okay, so let's think about what is. An angle of depression is when you have a horizontal line, all right, and you measure down from that horizontal. This angle here is your angle of depression. Okay, so knowing how to draw that diagram would be really, really, really important. Wink, wink, if you know what I mean. Okay. Angle of depression has to be measured from the horizontal. It's not just some angle that's facing down. All right. So make sure you know the difference between those two. All right. But as it pertains to this particular problem, let's sort of backtrack a little bit and think about what trig function we should use to find theta. All right, so we've got theta, we've got a 5, we've got a 2. What trig function is this like begging us to use here? Inverse sine. Okay. We could even start like this. Okay. If you're like, I'm not really sure yet, we could start with sine of theta equals opposite over hypotenuse. Right. And we could start with that because we have a number for the opposite and we have a number for the hypotenuse. And just like the previous question, we can go ahead and fill in the numbers we know. Okay. If we were to fill in the numbers we know, we get sine theta equals 2 over 5. All right. How do I get rid of the sine? If we have sine, turns out from our whole big table that we took a look at earlier, how do we find the angle? we get rid of sine using inverse sine. Okay, we get rid of sine using inverse sine. Now, similarly, we get rid of cosine using inverse cosine. We get rid of tangent using inverse tangent. Okay, so it is finding the angle, but it allows us to have a way of like getting rid of tangent, or getting rid of cosine, or getting rid of sine. Okay, so if we scroll back down to our question, if I want to get rid of the sine, then I'm going to inverse sine both sides. So if I inverse sine the left-hand side, I'm inverse sining the right-hand side. Okay. And I know that this notation might look a little intimidating, but we're basically doing like, oh, if we add 2 to both sides, or we subtract 5 from both sides, or we divide both sides by 3, whatever we're doing, we do to both sides of the equation. That's all we're doing here. Okay. But what this allows us to do is now the inverse sine and the sine sort of undo each other. And we're left with theta on the left-hand side. And on the right-hand side, we have inverse sine of 2/5. Okay. In Desmos, you can type that as just sine with a -1 in the exponent. All right, so I'll give you a moment to figure out how to do that. If your exponents in Desmos, you can use the caret button, which I think is above the 6 on the keyboard, right? But that will help you move something into the exponent. And let's see if we can confirm a value for this angle. All right, let's go to 3 decimal places if possible. Anybody confirm Ian's answer though with the 23.5 something? Perfect. All right. And I love that, Ian, you put in the units there, because 23.578, it's not feet, it's not inches, it's not any of those things. It's the angle. And when we're working in like word problem situations, more than likely we are working with degrees. Okay. Now, same thing again, if you got a different answer, it might be that somehow your calculator went back into radians and you just have to change that again. Okay. But I wanted to use this question to highlight a few different things. One, that we have to read very carefully about where we label things. Okay. Again, maybe on a quiz, we lost like 1-2 points because of that. You will lose more on an exam if you don't label things properly, because we've had some time to marinate, and now that's sort of a new expectation. Okay. As far as the setup goes, you can use the same setup. The idea that's a little bit different is just how do you get rid of the trig function, right? And you get rid of it by looking for the inverse of it, right? That's where we get the inverse on the other side, and then we just have to use our calculator to find that value, right? The last thing I wanted to really drive home here is please look up some examples on that angle of depression, all right, and how to use that to solve a problem. I think you'll find that to be very beneficial before you walk into the exam on Wednesday, okay? All right, so here's what I want to do. I want to take a look at just this little table right here. I'm going to talk about this table a little bit, and then we're going to take a break. And then when we come back, we're going to do a bunch of examples. Okay, these examples are going to be broken up into like 3 different categories. And so as we go through the examples, it would be really important for us to think about decision making. How do we know when to use what strategy? Okay, and you're going to hear me say that so much in this course, right? So much of this is about that decision making. And I think some of us are starting to feel like, wow, I can't memorize everything anymore. And so there needs to be a level of sort of understanding so that we can move through the curriculum. Okay, and that is actually a reality. It's also going to be a reality of Math 150 in the spring. So I really want us to just kind of start to embrace that idea. Okay, it's a very different way of thinking, but I promise you that my goal here is to set you up to be super successful. All right. All right, so let's talk about the 3 inverse trig functions that we've talked about, or that we saw at that table in the beginning. All right, so the first one here is something called inverse sine, and we've seen that we can write this as like sine with a -1. Okay, maybe a little bit less familiar or more familiar, depending on what teacher you had before. Sometimes this is called arc sine. It's a different name for the same thing. All right, so some people will say inverse sine and other people will say arc sine, but they mean the same thing. Okay, so you can write it like sine with a -1, or you can write out more letters and have it be arc sine of x. All right. Similarly, we have inverse cosine, which we can write as cosine with the -1, or another way of writing that is arc cosine, and we can say arc cosine of x. I will likely go between the 2 just to get us familiar with that. It's intentional that I don't always use the same one because I want us to be familiar with both of them. Okay. Last one we have here, inverse tangent. It could be the tangent with the -1x, or arctan is a longer way of writing it out, but either way is fine. Okay. So equation wise, that is what we have for our 3 inverse trig functions. All right. Now it's been a while since we've talked about domain and range, and you can groan silently or feel however you want to feel, but as promised, domain and range will not go away. In fact, we're still going to see them in Calc 1. You'll still see it in Calc 2. And so it's not out of like punishment that I keep bringing these up, but is more of like, these are things that we are going to see. It's like a reality of the situation as STEM majors. And so, you know, I don't want to give you false ideas that you don't need this. Okay. But if we think back to what domain means, maybe one of the things that comes up for us is that domain is like all of the x values and range is all of the y values. Okay. And so if we think about what we have here, the domain of the inverse sine is bracket -1 to 1. And what that means is that on a graph, you can see that it starts at -1 and it stops at +1. Okay. There's no arrows on this graph, by the way. I'm not just showing you like a small piece of it and it keeps going forever and ever. Okay. This is it. That's the graph. It's just, whoop, that's it. Okay. The range in this case is -π/2 to π/2. And we can see that the y value down here is -π/2, and the y value up here is +π/2. Okay, and our graph literally ends right here and it starts way down here. So that's it. There's no arrows. It doesn't go on forever and ever. It's literally a tiny, tiny, cute graph. That's it. Okay. But let's see about inverse cosine or arc cosine. The domain here is -1 to 1. And when we look at our graph, we start at -1 and we end at +1. Okay. But the range or the y values is a little bit different, right? And in fact, I have a typo here that I'd like to correct. This is not pi/2, it is pi. And from our graph, we can see that we start down here at 0 and we go all the way up to pi. So just like the other graph, the arc sine one, we have a starting and stopping point. It's a tiny, cute graph. That's it. Okay. Oops. All right, let's move on to arctan or inverse tangent. And we can see here that this one has a domain that is different from the other two. Its domain is from -infinity to +infinity. And so what that actually means is there are arrows on the ends of that arctan graph. Okay, the arctan one is not as cute as arc cosine or inverse sine. It does stretch out forever and ever in the x directions. Okay, let's see if we can see the range here though. And one thing I want us to notice about the range is that these are parentheses and not brackets. What that means is that at x or y equals pi/2, we sort of have a dashed line like this. What are those called again? Anybody remember from Math 116? What are those called? And in particular, what kind is this one? I agree that it's an asymptote.
Horizontal.
Exactly. It's a horizontal asymptote. Perfect. Okay. Now, if I have a bracket or a parentheses on the -pi/2 one, that means I must also have another horizontal asymptote down here. So the arctan or the inverse tan is special because it has two horizontal asymptotes. All right, it has two horizontal asymptotes. One is y equals -pi/2, and the other is y equals +pi/2. Okay. All right, let's see. All right, so I'm going to stop sharing this screen, but I'm going to reshare a different screen on Desmos. All right. Where did I get this? Make it go away. Okay. So I'm going to stop sharing this. I will share my screen, a different screen. Okay. So we all know that we can use Desmos to graph things, and like that's pretty useful. We can use it as a calculator, and that's also really useful, right? But sometimes it's nice to know that Desmos can do like some fun things or things that make the platform just more accessible, okay? So in here, I've typed in y equals inverse sine of x. Now, knowing that I just did the range as like pi values, should I be in radians or degrees to get this picture? Yeah, I want to be in radians, right? So we were just in degrees, and we're going to go back to the graph setting and make sure we're in radians, right? Because if we're in degrees, we might get a picture that kind of looks like this. But if we want to match the radians, we've got to click radians, okay? Now, I don't know how many of you have a Mac. I think whatever the option button is, if I click Option T, you see how this changes the menu down here? And now I have something called Here Graph, okay? I think this is pretty cool. We're going to use this again when we look at graphs of like sine and cosine. But what we can do is hear what this graph sounds like. And I think this is great for people, probably designed for people who maybe struggle with their vision. Maybe they can't see the graph, right? But I think as a tool for all of us, sometimes we just need things that are helpful in remembering things. And so maybe one way is thinking about the way a function sounds, all right? So let's see what this looks like, or what it sounds like. Okay, so that is Desmos's interpretation of what sine of x looks like, or inverse sine. But if I tried inverse cosine, right, and I change that menu again, do we think it's going to sound the same? Like before I click play, what are our thoughts? Is it going to sound the same as inverse sine, or is it going to sound different from inverse sine? Maybe I could.
Different.
Right. So we can see the purple one is the inverse sine and the green is the inverse cosine. So let's just turn that one off for right now. And let's hear what this one sounds like. Right? This function is decreasing. It's going down. And so like Dallas said, it's going to get like lower in volume or maybe get quieter or lower in pitch, right? And so let's think about what inverse tangent sounds like, right? We can see already if we put all three graphs together, we can see that like we have this cute green inverse cosine, we have this cute purple inverse sine, and then we have this inverse tangent that is so much bigger than all the other graphs. But we could hide the other ones and we can do that. Option T is how I'm doing it on a Mac. I'm sorry, I don't know what the command is on a PC to get this menu to show up, but we can click play on inverse tangent and think about what that's going to sound like. Right? And if you make your window bigger and bigger, then it will make the sound go a little bit differently. But if you zoom in on specific parts, then it'll sound differently. Okay, so I think this is actually a super cool way to think about this because we're going to see so many different graphs that like at some point, maybe we can memorize things, but maybe just having these different sounds might be a way for some of us who are like, it's been really hard for me to memorize, but like, I'm a really auditory person. And this is something that maybe you can take with you, right? So I did want to show you that pretty neat feature of Desmos. We are, as promised, going to take a break. When we come back, we're going to go through a bunch of examples. And again, I cannot stress how important it is for those examples for us to think about like, the reasoning. Why do we get the answer we get? And how do we know to start those or recognize that it's that kind of question? Okay, so I'm going to stop sharing my window here. I'm going to go ahead and pause the recording. Where did that button go? Recording. Great. Okay, so a couple of things that I want to talk about. So again, I said earlier that we're going to do sort of different categories of examples today. And while we're in lecture and it's like the first time you're seeing things, of course, it's all going to be in like grouped by type, right? But as we study for an exam or really want to master something, it's really useful to sort of mix and match those different things. So we're studying in a bigger context, okay? And so one thing you'll notice is that for all of these questions, I'm going to say, I want you to evaluate these without a calculator. And that is something that I'm going to be very adamant about. So no calculator while we're sort of here in lecture. I clearly cannot control what you do in the privacy of your own learning environment, but when we are in the exam, again, there will be parts that are non-calculator. And so as we're going through this, I want us to make sure that we're really mastering the concept and the process so that we do know how to do this without a calculator, okay? One note, be sure that your answer is in the range of your function, right? So earlier before break, we talked about the range of different functions. And so I want to go back up real quick and sort of take a look at those so we can note those down before we continue on the practice problems, okay? So in particular, things that would be really important to notice here are the range for inverse sine is from negative pi over 2 to pi over 2. The range for inverse cosine is 0 to pi. And the range for inverse tangent looks almost the same as inverse sine, except it has brackets, or it does not have brackets, rather it has parentheses. Okay. So if we note those down, we could say that for inverse sine, we have from negative pi over 2 to pi over 2, right? Can someone tell me, if I asked you to go from negative pi over 2 to pi over 2 on the unit circle, let's actually make these two up here. Okay. If I asked us to find negative pi over 2 to pi over 2 on the unit circle, where would you look on the unit circle? Wow, that's a terrible circle. Good. All right, so I'm asking a lot of questions today because I definitely want us to be thinking and reviewing like content that we've seen in the past. Okay, so it is intentional. I know we have an exam this week and I'm asking the questions because I want to sort of help us start to practice and study for that. All right, so where does negative pi over 2 to pi over 2, where on this unit circle would I find those angles?
There's a pi over 2 at like the right angle 90.
Yeah, I would agree with that. Okay, so let's start. I agree that pi over 2 is like up here, but where is negative pi over 2?
At 3 pi over 2.
Yeah, right. We talked about how to find those negative angles, and this is another case where we might need to look for those negative angles, right? We go to the positive version of it, which is up here, and then that negative means we reflect it down here, okay? And so if I want to find the angles that are from, I start counting at negative pi over 2 and I stop counting when I get to pi over 2, I'm going to start down here where this yellow, let's pick a different color. I'm going to start down here where this blue is, and I would go all the way until I stopped at pi over 2. So in other words, I'm really choosing from the left or the right-hand side of the unit circle, okay? Now, if we apply this to inverse cosine, and we know the range is from 0 to pi, where would I start and where would I stop? I can hold the silence real long. All right, this is not about me answering these questions because I'm not the ones taking the exam on Wednesday, okay? Yeah, we would highlight the top half exactly because we're starting at 0, right? We're going all the way to pi. Perfect. All right, so we're taking a look at this. And we only want to choose answers that are from the top half. Okay, that's why that's going to be important for us. All right, well, what do we do about this arctan situation? Where would we choose values from there? Yeah, it would be the same as inverse sine. Oops. So we would choose from this right half of the unit circle, right? So when we're answering the questions on the next page, we need to be really careful about picking the right answer, all right? When we took a look at this same concept on Monday of last week, we always had 2 answers, but now we're only going to have 1 answer now that we've learned something new, okay? So let's keep those pictures in mind and think about this first question here, right? So this first question says inverse sine of √3/2. And we know from last week that when we see this -1, that our answer is going to be an angle. All right. Last week, though, there were 2 answers, but now there's only going to be 1. Okay. So I see sine here. So what does that tell me about what value I'm looking for? X, Y, X over Y, Y over X, 1 over Y, 1 over X. What value are we looking for here?
Y.
So we're looking for Y. So I'm going to go ahead and write that there. And the Y value is, what is the Y value we're looking for? Yeah, the Y value we're looking for is √3/2. Great. So let's pretend for a moment like we were last week. Find me the Y values on the unit circle that have a value of √3/2. All right, give me both answers there. So from our unit circle, which you should always have with you in your brain or in your heart or on a piece of paper, what angles have Y values of √3/2?
Pi over 3.
I agree. Pi over 3 is one of them. And yep, I think the other one is going to be 2 pi over 3. Okay, so we've got, let's see, how should we write this? Pi over 3 or 2 pi over 3, right? That was the way we answered this question last week. but in all capital letters, I was like, be sure your answer's in the range of your function. So if we were to take a look back at these pictures, since I'm looking at inverse sine, I can only choose from values that are between negative pi over 2 and pi over 2. So which one of these answers is not on the right half of the unit circle? Great. 2 pi over 3 is over here, right? So I'm going to come back down to the answers, and I'm going to put a green circle around pi over 3 because this is in the range, but I'm going to put a big red X through 2 pi over 3 because it is not in range of inverse sine. Okay, it's not in the range of inverse sine. All right, let's try another one. Let's try example 4. So example 4, tell me what I'm going to fill out in these first 2 lines right here. The what value is what? What do I write there? Yep, the y value is -1/2. Great. I know my answer is going to be the angle because of that -1. So let's go to our unit circle. Let's find the 2 angles. Oh, is it not updating? Ah, there we go. Thank you for letting me know. Great. Okay, so the y value is -1/2. Give me the 2 angles where that happens.
$11 pi over 6.
Yep, 11 pi over 6 and
7 pi over 6.
great. 7 pi over 6 or 11 pi over 6. Wonderful. Okay, so this is sine, right? Inverse sine. So I have to choose from values on the right half of the unit circle. So which one of these values can I put a red X through? 7 pi over 6 or 11 pi over 6? Which one is not on the right half of the unit circle? Great. 7 pi over 6 is not in range. Okay. But if you put 11 pi over 6 as your answer, I'm going to tell you you're wrong. Why would I do that? This is our almost answer. We'll put an orange next to it for like almost. Okay. 11 pi over 6. That is here. It's in the right place, but it's not the right name. I can only choose values between negative pi over 2 and pi over 2. And 11 pi over 6 is like bigger than pi over 2, right? This is really saying I can only have answers between negative 90 degrees and 90 degrees, right? If we thought about it in degrees, we would say we could only choose from negative 90 degrees to 90 degrees. What is 11 pi over 6 in degrees?
$330.
330, right? So if you tell me, oh, it's 11 pi over 6, then what you're really saying is 330 degrees is between negative 90 and 90. And I know all of you would look at me like I was crazy if I was like 330 is between negative 90 and 90, right? If you counted all the numbers between negative 90 and 90, you wouldn't get to 330, right? That's past 90 degrees. So what do we have to do? We actually have our almost answer. And then what we have to do is we have to rename our angle. Give it a name that is between negative 90 degrees and 90 degrees. Let's do this in degrees first. This angle here, that's like 330 degrees. What's another name in degrees for that angle? Maybe something that's between negative 90 and 90. Negative 30 degrees, right? We could, hey, there's that negative angle thing. We could count in the other direction, negative 30 degrees, right? Well, what do we call negative 30 degrees in radians? Negative pi over 6. And I saw someone else had that answer as well. So that is wonderful. We want to rename it negative pi over 6. And then we can say, yay, now we have the right answer. Okay. The inverse trig functions are a little bit trickier to work with because we can only choose certain value. Okay. So I would encourage you to do a lot of this practice before Wednesday so that it's a process that you feel comfortable with in terms of how do I know what the right answer is. Okay. So let's keep going. Let's try a few more and see. All right, for 5 and for 6. So inverse cosine or arc cosine for both of them. What do I put in that first line for both of these? Yeah, we're going to put an x value, right? Because we're not looking at inverse sine anymore. We're looking at inverse cosine. All right, so the x value for number 5 is going to be 1. And let's find the angles where we have an x value of 1. Give me both names that we have.
0.
Great, I got 0 and 2 pi. Great. Which one of those is out of the range for inverse cosine? 2 pi, exactly, because the range of inverse cosine is only from 0 to pi. So this one is our correct answer, and the 2 pi is not in the range. All right. Great. For number 6, I'm looking for an x value of -1. Give me the angles where we have an x value of -1. Great. We have pi or -pi. Which one of those is not in the range? Yeah, not in range, but 0 all the way to pi is the range for inverse cosine. So we have our pi as our answer. Okay. All right, let's take a look at some of the more beefy ones here. All right, questions that take a little bit more thinking, all the tangent ones. You'll notice that I put a bunch of the tangent ones in there because I want us to practice them. All right, too often people are like, oh, I got sine and cosine, I just don't know how to do tangent. And that doesn't serve them very well in the long run. Okay, and I want you folks to be prepared for those challenges and walk in and be like, I do know what this is, and I can tell you how we found it. All right. So let's start with example 7. We're looking for the inverse tangent of root 3. That means I'm looking for the y over x value of root 3. Okay. Which angles have a y over x value of root 3? I disagree with that, Ian, unfortunately.
Pi over 6.
Say that again.
Pi over 6.
Pi over 6. No, all right, pi over 6. What would the other one be then? Oh, wait, sorry, Ian, you are right. I don't know what I'm thinking. It is pi over 3 and pi over 4 pi over 3. Sorry. Ooh. All right, but you, Ellie, have the answer for number 8 with the root 3 over 3, the pi over 6, or what would the other one be other than pi over 6? Yeah, 7 pi over 6. All right. Sorry for the confusion. All right, let's talk about which ones are in the range. All right. So for the inverse tangent of root 3, the one in number 7, which one of these answers can I cancel and say you are not in the range? Yeah, it's going to be the 4 pi over 3 that is not in the range. However, pi over 3 is between 0 and pi over 2. Nope, you're fine. I knew what you were trying to say. I got you. All right, what can we say about, for example, 8? Which one of these gets the big red X through it that we don't want to write down as an answer? Yeah, the 7 pi over 6. Okay, but this one, pi over 6, is correct. Right. All right, we got 2 more examples here. We have inverse tangent of undefined and inverse tangent of 0. All right, so I know in both cases we'll have y over x. And in example 9, I'll have y over x is undefined. And in example 10, I'll have y over x is 0. Okay. Again, tricky cases that we often confuse which one is which. In example 9, what am I really looking for on the unit circle? Yeah, we want to know where we're dividing by 0, because when we divide by 0, that is problematic for us. Okay. So where is cosine equal to 0? Good. We've got pi over 2 or 3 pi over 2. Which one gets the big red X? Yeah, this one is not in the range, but pi over 2 is. Great. And last question here, inverse tangent of 0. What are we really looking for here? where the sign is 0, right? The only way to get 0 out of a fraction is when the numerator equals 0. All right, so which angles have a sign of 0? Yeah, 0 or pi. Wonderful. Which one of those gets the big red X? Yeah, pi is too big, but 0 is perfectly between negative pi over 2 and pi over 2. Okay. So before we move on, I just want to see if there are any questions around this decision making, because we're about to add layers onto this. So if this doesn't feel good, the layers that come next are going to feel even worse, right? So let's take a moment and just kind of take a look at this, see if we have any questions coming up.
How did we rename the angle in example 4?
Sorry, say that again.
How did we do the renaming in example 4?
Why did we do it, or how did we do it?
How?
How? Okay, so we go to our unit circle and we say, oh, 11 pi over 6 is like right here, right? This is 11 pi over 6. But 11 pi over 6 is too big of a name, right? Because if we're thinking in degrees, we're calling it 330 degrees, which is bigger than 90. So we want to think, how do we name this in maybe a negative way so that we'll get a number that is between pi over 2 and negative pi over 2. Right? So what's another way that I can say 11 pi over 6 if I count in the negative direction?
Negative pi over 6.
Yeah, 11 pi over 6 is the same as negative pi over 6. So all we do is we say, ooh, this name was like too long. We wanted a shorter name for the same thing, but it just fits between negative pi over 2 and pi over 2.
Okay, that makes sense. Thank you.
Okay. Great. All right. So I see another question about examples 7 and 8. So here is, if you're not feeling confident about where these are coming from, that would be a really important thing. We practiced it a bit like the last couple of weeks, but I would go through, if you're not sure yet, I think it is worth the exercise to divide all the coordinates and see which one is which. Okay. I think that just trying to memorize is not always reliable, but if you can take some time to sort of divide the y and x coordinates and see what you reduce down to, I think that would be really useful. Okay. So for example, if we have a coordinate of like √2/2 and I divide it by the x value, right? I would practice doing that math and see what you get. But I would also practice, like, what if you have √3/2/1/2? Practice that, see what you get. And same thing with this last one. I would practice those and see what you get. Okay. I think once you do enough examples, then it'll be easier to remember which angles make that happen. Okay. And so it's okay if you're not there yet, but I think this is a good practice to do at least a few times in your mathematical career. Okay, you can always come back to this in case your memory fails you or something like this. But I would think about like how we just divide those fractions. Okay. All right, so let's go ahead and take a look at the next layer of questions. Okay. In fact, there's 4 of these, and you can see that they're a little bit different in structure from the last set of questions we did. Can someone describe to me what's different about questions 11 through 14?
We have like two functions used.
We do have two functions. That is a great observation. Okay, so numbers 11 through 14 have two functions. All right, that's one thing I agree. What is the same about all of these examples right here, 11 through 14? Like, what types of functions do they involve? They involve inverses, okay? Now, where are the inverse functions? Okay, so 11 through 14 have two functions with the inverse trig function on the outside and the regular trig. Okay. That is really good pattern observation. So let's think about how we solve these questions. But when we get to the next group of questions, we'll talk about kind of the same thing. Like, what do these questions have in common? What is different about them from the previous questions? Just so when we see these questions and they're all mixed and matched together, we can really zone in on like what type of question and what process we have to follow, okay? So let's start with example 11, okay? The way I want us to approach these questions is pretty specific because there are shortcuts, but the shortcuts often get people in a lot of trouble, okay? So I don't want to do the shortcut yet. I'd like to talk through sort of a longer way that will work with every single one of these problems so that we have something to really rely on, right? So in particular, the way I would like us to approach these questions is to start by finding an answer for just the inside part, okay? So if we take a look at number 11, my next line, I'm gonna write inverse sine, and then you're gonna tell me what is sine of 5 pi over 6, and I'm gonna replace that inside the parentheses. So using your unit circle, find sine of 5 pi over 6. All right, we have one value there for -1/2. Can anyone confirm or deny that value? Oh, we have conflicting answers. Can we get a tiebreaker? All right, I would agree. It is indeed 1/2. And I think particularly on exam day, it would be worth making sure that you just double check these values along the way, okay? So all I've done so far is answer this question, and I got that answer, right? So sine of 5 pi over 6 is 1/2. Now we're going to answer this question, okay? So now we have a question that looks pretty much the same as questions we saw in the previous page, right? Inverse sine of 1/2. So give me both answers that could possibly be true here, and let's go through that decision-making process again. All right, what are two answers, two possible answers for this? Great. So we have pi over 6 or 5 pi over 6, all right? Which one do we put the red X through? Which one is not in our range? Great. 5 pi over 6 is not in our range. Therefore, our answer is pi over 6. Okay. Great. Let's try that same idea with example 12. I'm going to want us to start by evaluating the part in the green. Okay. So we're looking for cosine of 5 pi over 6. I'm going to write the rest of the question. You tell me what is cosine of 5 pi over 6. Negative root 3 over 2. I agree. Great. Now we've turned this into a question that looks just like the questions on the other page. All right. So give me the two answers that are possible for inverse cosine of negative root 3 over 2. Can we get a confirmation for that? 5 pi over 6 or 7 pi over 6? Yes. All right. 5 pi over 6 or 7 pi over 6. Which one is our answer? Like, which one is in the range? Great. 5 pi over 6 is in the range. However, 7 pi over 6 is too big to be in the range. All right. Example 13. Let's start with the inside again. Inverse sine of what is cosine of 2 pi over 3? We've got one vote for a negative 1/2. Anybody agree or disagree? All right, negative 1/2. All right, which angles have a sine value of negative 1/2? Give me both options. Great. 7 pi over 6 or 11 pi over 6. All right, which one gets the big red X? It is out of the range of inverse sine. I agree, 7 pi over 6. So 11 pi over 6, is that in the range? No, so this is our almost answer where we have to rename it. If we don't rename, then we're saying 330 degrees is less than 90 degrees. And that is a silly statement, okay? So how do we rename this? Well, we can look at where that angle is and just give it the negative name. And that is negative pi over 6. Okay. So 11 pi over 6 is like our almost answer. But as mathematicians, we're never quite satisfied with an almost answer. We want the actual answer. Okay. All right, let's tackle this last problem here. Same sort of idea. Let's evaluate the inside part first. We go ahead and write the outside, which is inverse cosine. And I'd like you to find the tangent of 7 pi over 4. All right. This is a good chance to practice your fraction division, see what you get. All right, so if you go there and you find the X and Y values and you go ahead and do that math, or the computation rather, X over Y, I believe the Y value is negative root 2 over 2, and I believe the X value is positive root 2 over 2. Do we actually have to divide fractions here?
No, because it all equals 1.
It equals,
Out of 1.
yeah, it's going to reduce to -1, right? And in particular, we have that negative, but we have something divided by itself. And so if you're sitting here being like, how did people do that computation so fast? That's probably how they were able to look at that, okay? All right, so the question now really is, find the inverse cosine of -1. So what are our possible values and what do we get? Yeah, we could have pi or negative pi. And the negative pi is not between 0 and pi, but pi is. And so we get our answer. Okay. So we sort of zoom in on these 4 questions right here to get those all on one screen. That process that we did worked for every single one of them. Okay, start with the inside, work our way out, right? But a few things to notice here. Sometimes we have to divide, right, to find the tangent values. That's a fair request. Sometimes we have to rename things. And I will tell you right now that I will be asking you questions that involve renaming on the exam on Wednesday. So this is a very important skill that I want you to know and be able to execute. All right. And last but not least, if we look back at example 11 and 12, right? If we look at 12, this is where some people try and shortcut things. They see cosine and inverse cosine. They're like, great, I'll just cancel them and I get 5 pi over 6 as my answer, which it was our answer. So in that case, the shortcut worked. But if I go back to example 11, inverse sine and sine, that would mean I would get an answer of 5 pi over 6, but I didn't actually, I got pi over 6. All of that is to say, if you follow this process, you're not going to get the wrong answer. But if you try and shortcut things, sometimes you'll get the right answer, but sometimes you won't. All right. So I would really prefer that we always know how to get that right answer than sort of just guessing and hoping that we get something that's right. All right. All right, so let's take a look at 4 more examples. All right, again, different in flavor, but let's talk about how they're different. So let's take a look at 15 through 18. Can someone tell me how these are different from the previous questions we've looked at? All right, so I see that the inverse functions are now on the inside. Well, where were they before? They were on the outside. Okay, so the fact that we have inverse functions in different places might mean that we change our strategy. Okay. And that's really the key difference I wanted us to notice there, that in these cases, we have the inverse trig ones on the inside. And it turns out that we can solve these problems just by drawing and labeling a triangle. Okay. So here's what we're going to do. Let's choose another lovely bright color, maybe neon pink. And we're going to do the inside part first, but we're going to use that to draw a triangle, right? So right triangle. All right, I'm going to copy and paste this before I write all over it. Great. Okay, so where do you want to label the theta? And I will tell you this part, it doesn't matter, but where would you like to label the theta? All right, so we'll put the theta down here, sort of a comfortable and natural place that we've seen theta quite a bit. Okay. All right. Based on this, where do I put the numbers 3 and 5? Okay, so 5 is the hypotenuse. Great. Where do I put the 3? Okay, where does it go though? The horizontal side or the vertical side?
The vertical side.
Ooh, competing answers. Who's got the tiebreaker?
Oh, wait. The horizontal. I was thinking of sine.
Great. Yeah, and it's easy, right? Because I wrote sine right here. So aggressively highlighted in the pink, we want our adjacent side to equal 3. Great. All right. Well, how do I figure out the third side of my triangle? It is a special triangle, right? And knowing that this exam is going to be a lot of non-calculator, you can bet that a lot of the examples I'm using are going to be nice, special triangle values. In particular, this triangle, what is the length of the opposite side? 3, 4, 5. Exactly. So that opposite side is 4. Okay. I can imagine it feels like I'm asking you to memorize a lot and I'm telling you, oh, this is important, that's important, and we're going to use this again, and we're going to use that again, and it can feel super overwhelming. I think that maybe we consider that part of what I like to call the hidden curriculum in a lot of math classes. Hidden in the sense that, like, can you sit and do Pythagorean theorem for this? For sure, right? It's not mathematically wrong. But as we sort of embark on new journeys with new content, sometimes we don't want to sit and spend our energy doing Pythagorean theorem. The problem will go a lot faster if we're like, oh, this is a 3, 4, 5 triangle. I recognize that, right? It's like an extra 3 minutes back on your, work or whatever. But a lot of times when you have a professor who's like, no calculator, that seems really mean, it's because they're trying to like encourage you to use these values, right? And if you get to like a higher level course like Calc 2 or maybe Calc 3, sometimes this is just the tiniest piece of a problem, a very, very long problem. And so we don't really, it will take us much, much longer to get to that end point if we have to do all the little computations along the way. Okay, so I know we're all sort of different majors in here. We have different depths into which we're going to dive into this math world. But I know at least in the immediate future, like a 3, 4, 5, being able to recognize that is definitely going to pay off. Okay, so it's okay
Wait, but then
right now, but there is a reason behind it. Sorry, what was the question?
How did you find the 4? I'm confused on that.
So in one of our lectures, we talked about special right triangles. I was like, I would recommend that you memorize these. 3, 4, 5 was one of the special triangles.
I'll look back on the notes then.
Okay, so 3, 4, 5, meaning if the legs are 3 and 4, that the hypotenuse has to be 5. Okay. All right, so we have this diagram now. We're going to use the diagram to answer this question. Okay, what is sine of theta? Right, this question is really asking us, what is sine of theta? So when you look at your right triangle here, what is sine of theta? It is not pi over 6. It's not pi over 6. I argue that you can actually answer the question just by looking at this. Yeah. Matthew, how'd you get that? 4 over 5. Exactly. We go all the way back to the things we talked about on the very first day, right? So sine, everybody knew SOHCAHTOA, and sine was opposite over hypotenuse, but it comes back. If I'm looking for sine of an angle and I have a picture of a right triangle, just looking for the opposite over hypotenuse, that's it. Okay. So even though this question looks like kind of scary and like a lot of different things happening, you could have actually answered this question on the very first day of class, knowing what you know about sine and cosine, right? Maybe we would have done Pythagorean theorem to find the missing side, but now we know there's a Pythagorean triple, or what was the other word for it? Pythagorean primitives. That's a fancier word for it. That is sort of a nice numbers to know so that we can sort of move through, focus on the concept rather than computation. Okay. So it turns out the answer to this question is 4/5. All right. And we did that by drawing a picture with the inside part, and then using what we know about SOHCAHTOA to answer the outside part. All right, let's try another example here. All right, so we've got, I'm going to go ahead and copy and paste this again, just so I have it for later. All right, so, whoops, where should we start this time for example 16? What do we want to work with first? The inside part, just like the other problems, all right? All right, so we've got our right triangle. Where do we want to put our theta? Okay, let's put it on the top this time. That's fine. You can put the theta here, or you can put the theta up here. You just can't put it where the right angle is. Okay. All right, well, based on where we drew the theta, where should I put the 12 and where should I put the 13?
The 12 should go on the bottom because it's the opposite.
Love it. And the 13? Yeah, the diagonal, right? So 13 equals our hypotenuse. Great. All right. This is, I argue, another Pythagorean triple. even though the numbers are bigger. This is one of the few right triangles where we have whole numbers on every single side. So 3, 4, 5 was one of the triangles that I said was like a good one to know. Anybody know what this one is? It is not 7, no.
I've
Sorry, I don't know what's going on with the screen share. Anybody know what that third number is though? Something 12, 13. Yeah, it is 5. You got it. All right, let's try this share one more time. How do we find the length of that missing side?
I mean, it's difficult because we don't have any other value nor the angle.
Okay, but tell me about the process.
Well, I would use cosine to find the adjacent side over 10.
And I would agree, then you have too many things you don't know, but you have a right triangle, right? You have a right triangle. What other ways do we know about finding sides? Oh, there is a blast from the past, right? We do have our good old a squared plus b squared equals c squared, right? What do we put in for a? Or what could we put in for a? Okay, maybe we put in x, so we get x squared plus, what do we want to put in for the star side? Great, so b squared equals, what do we want to put in for c squared? Great, so 10 squared. Right, so instead of a squared plus b squared equals c squared, we have x squared plus b squared equals 10 squared. Great. How do I get b all by itself? Minus the x squared, and then? Okay, so we have b squared equals 100 minus x squared, great. So how do we get b? B equals?
Minus x.
Ah, that is precisely the wrong answer. I'm so glad you said that though. All right. Okay. This is not equal to that, but it is equal to the square root of 100 minus x squared. Okay. I am super glad though that you said 10 minus x, because that is the most common mistake. Okay. The issue here is we cannot just square root terms that have like a plus or minus in them. Pick a value for x, like let's say x equals 1, right? If I plug it into the pink equation, I get 100 minus 1, which is 99, and then b would be the square root of 99. But if you plug it into the other equation, b equals 10 minus x, it would be 10 minus 1, we would get 9. But 9 is not equal to square root of 99. Right? So even by plugging in numbers, which I think is a really useful thing to do, we don't get the same values. All right? So that's why we can't simplify it like that. But what this allows us to do is now we have our adjacent side, that is square root of 100 minus x squared. And even though I don't know what that is as a number, I can put that over here in the numerator. And I have an answer that has an x in it. And that is okay. All right. So let's talk about like a real world example when you would actually use, like, why would you want an x in an equation? Like, why wouldn't you want your answer to be a number? And so one of the best examples I can think about is like, let's say you're trying to figure out like a range of acceptable answers. So let's say you're trying to calculate what grade you need on that final exam to, well, we don't have a final exam, but what grade do you need on exam 3 to get the grade that you want in this class, right? You don't want it to be an exact number. You want to know, oh, this is like the range. Like if I get higher than this grade, then I know that I'll get the grade that I want, right? And so if we think about the way this works, because I have an x in this equation, that's the same thing as saying there's a few values that work for x, and I can try all of them and they'll make the equation true, right? But the ones that don't make the equation true would be values I don't want to plug in. So it's actually more powerful because it's like an equation that works for a bunch of values rather than something like 12/5, which is just one value. Okay. So even though it looks scarier to have the variable here, what we're really saying is, okay, well, let's make sure that we can answer this for like a series of values. Okay. Does that kind of make sense? Like what would make that more powerful? Or instead of having just a single answer. Right. Well, let's try a different example just to make sure. We'll try number 18, make sure we understand at least the process in terms of how we do this. But let me open up another whiteboard. Right, so example 18, oops, we have sine of inverse tangent of 4x. Now, what does that mean at the end? I'm going to be looking for sine of theta, which means what two sides am I going to want to know in my right triangle to fill out for my answer?
Opposite over hypotenuse.
You got it, opposite over hypotenuse, right? So I'm going to want that at the end of the day. Okay, so let's draw another terrible right triangle and label it and see how things go. All right. It doesn't matter where you put your theta. I'm going to put mine up here just to mix things up a little bit. Where do I put the 4x? Okay, so we're going to put a 4x, the opposite. Now, tangent is opposite over adjacent. So what number do I put in for the adjacent side? Yeah, we're going to put a 1 here. Okay, so this is actually a really important thing to look at. This 4x looks like it's not a fraction, but actually it's like 4x over 1, right? We can turn anything we want into a fraction just by putting it over 1. Okay, so how then do I find the hypotenuse? Because I need the hypotenuse to answer my question, right? I know part of my answer is 4x. But how do I find that hypotenuse? Great, so let's do that. All right. I'd like you, in the privacy of your own learning environment, to tell me what you get when you solve for that hypotenuse. Or what we should plug in where, right? So maybe we can kind of do that together. A squared plus b squared equals c squared. What do we plug in where? Do we know a value for A or B? What do we know?
It can be 1.
A can be 1, great. So 1 squared plus, what does that make B then?
4.
Good. So look, I'm going to put parentheses around that 4x. Okay, I think that would actually be really valuable. And then c squared is what we're looking for. Well, we're looking for c, right? Okay, so 1 squared is 1 plus what's 4x squared?
$16x squared.
Good, 16x squared. I'm so glad that you remember to distribute that square there, right? And we're looking for c squared. So how do we get c all by itself now that we have c squared? Right, how do we get c? Great, so we'll have square root of 1 plus 16. And we maybe want to leave ourselves a note that it is not. What would a wrong answer be here? Yeah, so instead of 1 plus 4x, that would be wrong. Okay. So we can go ahead and put this square root, of 1 plus 16x squared right there. And that would be our solution. Again, more powerful because we can plug in some values for x to see what works and what doesn't, just like when we play like that game of what grade would I need to get the grade that I want, right? All right, well, I apologize for the technology fail towards the end here. Even though it's messy, we're able to sort of make that work. But that's all we have for today's lesson. So I'm going to stop the recording.